Hello everyone, welcome to lecture 4 of week 9 of the course Power Network Analysis. This lecture is going to be the second lecture of the module Fault Analysis. The previous lecture we talked about the variation in the synchronous machine reactance just after a fault in the sub-transient period, transient period, and finally how it achieves its maximum possible value in the steady state period. We'll discuss or continue on similar lines this machine parameter variation behavior. In fact, in the previous lecture, we had assumed first that the synchronous machine's armature current would have a typical signature where in subtransient the current is at its maximum, then followed by a dip in the transient period, and finally the least possible RMS value in the steady state period. Assuming that we had understood the synchronous machine parameters variation in the previous lecture, we'll discuss about that particular assumption, that why it happens from the machine armature currents perspective just after a fault, and we'll discuss about that in this today's discussion. So we have concluded that for a well-designed synchronous machine, when armature resistance is almost negligible, the overall armature circuit is an inductive circuit, and hence the armature current tends to lag the internal EMF or terminal voltage almost by 90 degrees, depending on the loading condition. And for salient pole machines, the direct axis reactance is the maximum, the quadrature axis reactance is minimum. So we are neglecting the effect of the presence of quadrature axis current for the sake of simplicity in our discussion. And because the machine has variations in the corresponding synchronous reactance, XD double dash, which is a subtransient reactance, is the minimum just after a fault, followed by an increase in the reactance, which is XD dash. And lastly, the steady state reactance, which we have discussed or talked about in the steady state analysis of synchronous generators. We have so far not understood the importance or application of XD double dash and XD dash in any of the modules that we have talked about. So all this was true assuming that the armature current of the synchronous generator has some typical signature, which is the signature being that the current is maximum and then it tends to go down as the fault period persists. So why is this assumption? I mean, what is the basis for this assumption? How do we defend it or understand it mathematically? Can we understand that? Yes, there is a way. Since our synchronous machine or generator is mostly an inductive circuit, so we can understand the current behavior of the armature current, the armature current behavior basically for the synchronous generator. The way it behaves during a fault or just after a fault or in the steady state period, the same can be analogously understood by the response of a series RL circuit. Why RL circuit? Because our armature circuit is mostly an inductive circuit. Resistance is not exactly 0, but for a well-designed machine, the value of R can be considered to be 0 or close to 0. So our series RL circuit here refers to or has equivalency with the armature circuit or stator circuit of the corresponding synchronous generator. So if we can understand how the series RL circuit responds to certain switchings with a terminal with a voltage source VT applied to it, then the same logic would also be true for a synchronous generator which is actually unloaded in the beginning. So what we have here is a RL circuit, some non-zero R, some non-zero L, which is also getting excited by a voltage source V of t. V of t is given as root 2V sine omega t plus alpha. So this is time varying form of V of t. The corresponding phasor form, if you recollect our per unit analysis or basic circuit principle analysis, the corresponding phasor representation of this time domain quantity would be V at an angle alpha, assuming that sin omega t is the reference for conversion from time domain to frequency domain representation. So alpha is some phase angle with respect to some reference phasor. Alpha could also be chosen as 0, it could be non-zero depending on what reference has been chosen. And at t is equal to 0, so basically this is before t is equal to 0, at t less than 0, the circuit is unenergized, just unenergized, because there is no path for this I of t current to flow through this circuit. At t is equal to 0, this switch is getting closed, and as the switch is getting closed, the circuit is now energized because of this voltage source present, and we wish to find the expression of I of t as a function of time. We are not retaining or going to the phasor domain, although the circuit can also be analyzed in phasor domain. Please refer to the basic circuit principle discussion that we had, where you could also find details of phasor domain analysis. We are trying to retain in the time domain because of a certain behavior which we want to understand, which might not be captured in the phasor domain analysis. So we want to find the expression of I of t. Since at t less than 0, the circuit current is 0. So at just t is equal to 0 plus, the initial current is 0 because there was no path for this current to flow. It was unenergized. This serves as our initial condition. And the corresponding equation that we make use of is through KVL across the circuit after the switch is closed. So we get I into R, which is the voltage drop across this resistor. L di by dt is the voltage drop across the inductor. And since there is no other voltage source present except apart this V of t source, so these voltage drops by KVL should sum up to the voltage which is applied in the circuit. Now with this initial, so this is basically a first order differential equation with this initial condition, and if we apply closed form techniques to solve differential equations, first order differential equations, we can very well get this expression of I of t as the closed form solution. This expression has two unique components. One component, as can be seen here, the first one is a AC component, and it is in, I won't say in phase with the voltage which was applied. There is a phase angle now which has come in, which is gamma. This gamma depends on the overall power factor angle of the RL circuit, the circuit which was having an inductance L and value R as shown over here. So the gamma is the power factor angle or the impedance angle or of the overall circuit, which is depending on tan inverse omega L by R. And depending on whether L becomes 0 or R becomes infinity, this gamma can tend to 0, and only in that case this AC current will be in phase with the applied voltage. The RMS value of the current, AC current, is dependent upon the applied RMS voltage V and the corresponding impedances which appear in the circuit, which is, so basically this is the Z load equivalent which is carrying this current L, and this Z load is the corresponding RL circuit behavior of the overall series circuit. And then the second term which we have here is a periodic component. So basically the first component, which is AC, is a periodic component having angular frequency omega. The angular frequency depends on whatever is the source frequency applied over here. The second term which comes in, it is independent of, I won't say independent, but it doesn't have, so basically it is a periodic term. It doesn't have periodicity, doesn't have a wave phenomena, and in fact it has a exponential component or term with it, and we call this component or term as, decaying DC component. We'll spend some time on this terminology here, why it is called decaying, why it is called DC. The term DC can be very straightforwardly understood because of the fact that this component doesn't have any periodicity. It is an aperiodic signal. So basically our DC signals that we see, they also don't have any periodicity. A DC component signal will always have a same constant value throughout the time. But since this DC component is not just a pure DC, it is having an exponential component to it, and this exponential component is a function of tau. We call this tau as the time constant of the series RL circuit, which is basically ratio of L and R, and the unit of tau is also seconds. Why seconds? So basically this unit should match with the unit of L by R. Remember that for inductance L, the corresponding reactance is omega into L. So if I rewrite this, so omega basically has unit of ohms, omega has a unit of radian per second, and L has unit of Henry. So if I rearrange this equation, we'll have 1 by omega equal to L by X. So L has unit H, Henry, X has unit ohm, and on the denominator of this LHS term, I have radian per second. So if I work around the units, L by X tends to have a unit of second by radian. Since radian itself is a dimensionless quantity, so L by X essentially has a unit of time, which is second, and that's the reason why tau also has a unit of time. So this time constant tau dictates what is the decay component, or how is this aperiodic component decaying with time. So basically, if time tends to infinity, what would happen to e to the power minus t by tau? This term would tend towards 0. When t is equal to 0, e to the power minus t by tau would be equal to 1. So we would have the maximum DC value of this particular component present at t is equal to 0, which is the instant at which just the switch was on in this series RL circuit. And as time progresses, e to the power minus t by tau would start diminishing, and that is where the term decaying or diminishing part comes in. And hence, we refer to this entire term as decaying DC component, DC referring to the aperiodic behavior of the signal, and decaying because it is having an exponential term. So that's what the summary of this particular current is, that the current tends to have a steady state sinusoidal AC component and a decaying DC offset component. We also call the term as offset because the overall I of t, which in steady state would be equal to the RMS AC current, because at t is equal to infinity, the decaying DC component would be 0. At the instant of fault, or just after the fault, or just after the switching, the actual current I of t is being appended or being offset by this decaying DC component. That's what the term offset refers to here. The values of this decaying DC component, as well as the phase angle present in the steady state sinusoidal component, it all depends on what is this L by R. So higher the value of L is, higher would be the time constant. For more period of time, for more cycles, the decaying DC component won't vanish. If the inductive part is less or the corresponding resistive part is very high, the decaying DC component tau time constant would be lower, and in a lesser period of time, the offset can go away. Essentially, if I have been able to explain the nature or behavior of these armature current, analogous armature current in a series RL circuit, and if I were to plot this I of t as a function of time, if this is x-axis is time t, y-axis is I of t, at t is equal to 0, apart from the sinusoidal component, I will also have the DC component, because at t is equal to 0, e to the power minus t by tau would be equal to 1. So it would start with some peaky value, I of t. It would start with some peaky value, and as time progresses, this peaky value would start diminishing because of e to the power minus t by tau envelope, and finally at t is equal to infinity or t tending to be a very high value, I would start observing some RMS component in the steady state period. So this particular current signature is exactly the same signature which was discussed here in the previous lecture as well as in the current slide. The same armature current behavior is also observed in an unloaded synchronous machine. The unloaded term here is important because the RL circuit that we analyzed, it was an unloaded circuit. At t is less than 0, it was unenergized, so the synchronous machine was not carrying any current at all. The RL circuit was also not carrying any current at all in the initial condition. So for an unloaded synchronous generator or a machine, if it is subjected to some fault, it could be a short circuit 3-phase fault or any of the asymmetric fault, the current pattern would still have a similar behavior as was discussed here in terms of I of t having some peaky value at subtransient period, and gradually this subtransient period diminishes because of e to the power minus t by tau trend, and finally in steady state it reaches some RMS value. This same envelope, when compared with the envelope shown over here in subtransient and transient and steady state period, is exactly the same. Also, before I proceed further, if I have to really understand what is the maximum RMS current that I would expect in the subtransient period. So basically, if I of t is y-axis, t is x-axis, and I have to find the maximum peaky RMS value which can appear in this particular RL circuit, how do I find this peaky RMS value? The answer is very simple. Since I of t has two components, one is the AC component, the first term, the second is the decaying DC component. Let me erase all this. The second is the decaying DC component. So I have this AC component here, then I have the decaying DC component DDC, which is DDC, the decaying DC part present over here, DDC. So if I have to find the AC and DDC RMS values, what I would do, I would first focus on what is the RMS value of this AC signal. Recollect the phasor domain discussion that we had in slide number 4. If root 2v sine omega t plus alpha is the time domain representation, the corresponding RMS value in phasor domain is capital V. Similarly, for the AC component present over here, root 2i sine omega t alpha plus gamma will have the AC RMS value equal to I only. Now, this is the corresponding RMS value of the AC component. For the decaying DC component DDC, what is the RMS value? How do we find? It's a decaying DC component, it doesn't have any periodicity. So, essentially to find the RMS value of it, what we would do, we would take the maximum possible value of current that this DDC would contribute to. That DDC maximum particular value is root 2i. Root 2i does not have as such any periodic behavior with it. It can only decay. It cannot change or have periodicity with respect to time. So DC RMS, which is the maximum possible value that can appear, would be root 2i. And overall, if I have to find the maximum RMS value of I, which is the armature current or series RLC circuit current, at t is equal to 0 in subtransient period, then this would essentially be equal to square root of AC RMS square plus DC RMS square. Remember, why do we ask, why need to square and add them up? RMS itself means root means square. So basically you have to take up the square of individual RMS components, add them up and then take the square root. So if we do that, we have I square plus 2I square, DC RMS is root 2I, which essentially gives us I of root 3. This can be the maximum possible RMS current which can be observed at t is equal to 0 just after a fault in the subtransient period for a series RL circuit or for a synchronous generator which is unloaded. Please don't confuse this with the negative or positive sign present in this particular slide. Depending on the value of alpha and gamma, this negative sign can also become positive depending on at what instant the switching has happened. So, having understood this particular behavior, now we can understand the corresponding time periods or tau that we discussed, the tau being the term sitting over here, the time constant term. So, what is the time period tau that appears in subtransient, transient and steady state period? In the subtransient period, the time constant, which is in the order of few cycles, depends on the xd double dash value. And since in the subtransient period, not much of stator flux links with the rotor winding, more of it gets linked with the damper winding. So xd double dash, it's primarily affected by the damper winding reactance, and hence the corresponding time period is the minimum in the subtransient period, followed by an increase in the time period in the transient period because xd dash value has gone up, because now more linkage happens between stator winding and rotor winding. And finally, in steady state, the current settles down to some steady state value, and the value of steady state reactance xd has been achieved, which is the final linkage. So overall, having understood, so with this, I sort of conclude the logic behind the assumption that why the armature current would have this sort of a time behavior. And having understood this, the purpose or essence of understanding or learning fault analysis is to find the worst possible currents that can be encountered during a particular fault. We understood about one such fault current in context of slide 5, which was basically at the maximum asymmetric current component, maximum RMS, that can appear at t is equal to 0 in subtransient period after a fault is equal to root 3I. Root 3I coming in because of the RMS component I of the AC component, and root 2I of the decaying DC component, squaring and adding them up with square root would give us root 3I. The purpose is to find this maximum possible current that can come or appear in this particular circuit when faults occur. That is the purpose of fault analysis. And why is it important to know this? If we don't know what would be the maximum possible fault currents, how are we going to protect our system? The power system protection has relays, circuit breakers, switches present in them. The ratings of these devices, the settings of these devices would depend on what are these maximum short circuit or fault current that can appear in during a fault event. So basically a fault analysis is a subtransient period, because only during subtransient you would get the maximum fault currents. Power flow analysis is a steady state period, so essentially we don't go inside the machine. In power flow analysis, we refrain from going inside the machine. We pertain ourselves only to the terminals of the synchronous generator. So basically, in context of power flow for synchronous generators, we have been considering PV buses and slack buses. We understood or went into the logic of conversion of PV to PQ bus when the voltage control or reactive power control of synchronous generator is lost. But we never went inside the synchronous generator. We never ever made use of synchronous machine reactance in steady state. Essentially, most of the studies that you would go or encounter in power network analysis, rarely you would ever find the application of XD or XS in the steady state period. Only the values of XD double dash, which is a subtransient reactance, finds its application in fault analysis period, because using XD double dash only we will be able to find the maximum possible short circuit currents. This is all about the current module of discussion. The last module, which would be stability analysis, would be a transient period study, wherein we would understand that after a disturbance or a fault, will the system be stable enough to reach the steady state period? What we have not understood from the devil's advocate perspective, that instead of this envelope going down, isn't there a possibility that this envelope might go up? In stability analysis, we will try to find those conditions or situations where this envelope will tend to go up, specifically from the fault current perspective. And that is where the transient period important study would come in, because essentially if the envelope would go up, it would more or less start with a similar subtransient period where the current either has its peak in the subtransient for fault or has its minimum during the stability analysis for unstable conditions. And those stable and unstable conditions is what would be our would be our focus of study in the stability analysis. And hence, in that stability analysis, XD dash value would be important. For fault analysis, XD double dash values are important. Rarely you would find studies where XD and XS are used until and unless intently you want to understand machine behavior in steady state. So we'll conclude our discussion with a numeric example where we have a 100 MVA 20 kV synchronous generator connected to a 100 MVA 20 by 400 kV three-phase transformer. The machines, the reactances under different point of time are given. The corresponding time constants are also given. The transformer reactance is given in per unit, 0.25 per unit. Generator is operating at rated voltage and there is no load connected to it. That means it's an unloaded situation or an unexcited situation. We want to find or understand the importance of occurrence of a three-phase fault we have still not discussed what is this three-phase short circuit fault, but having understood the impact of symmetric faults, for symmetric faults, all the three phases would get equally affected. So if such a disturbance happens where all the three phases of transformer or the generator get affected, then in that condition, we have to find the corresponding sub-transient, transient, steady-state currents. We have to find the corresponding maximum asymmetric RMS current, which we discussed in slide number 5. And we also have to understand that if the circuit is now loaded with some load, three-phase load of 80 MVA, 400 kV, 0.8 power factor, then in the presence of this load, a short circuit fault occurs, then what would be the corresponding transient current being supplied by the generator? So for the first bit, we first figure out our base values. 100 MVA is common for both generator and transformer, so the same can be chosen as base apparent power. So if choosing 100 MVA as base apparent power, and base voltage as 20 kV, which is the machine rated voltage, because the machine is operating at rated voltage. So the base current on generator side is 2886.75 ampere. The corresponding current on the transformer secondary is 144.33575 ampere. We have made use of the turn ratio of the transformer to find the corresponding base current on the secondary side. This current serves as the base current on the primary or the low voltage side of the transformer. This is basically the HV side of transformer. The corresponding sub-transient, transient and steady state currents that we would find. So basically, how would the circuit look like? In the first two bits, the circuit is like there is a synchronous generator which is connected to a transformer, and there is no other load present over here in the unloaded situation. For the third bit, we have a transformer generator connected to a three-phase transformer, and then we have a load connected which is drawing 80 MVA at 400 kV. The rating of this transformer is 20 by 400 kV. The generator is also operating at 20 kV. So for bit A, this is our equivalent circuit. For bit C, this is our actual circuit. So in bit A and B, if a fault occurs at the terminal of the secondary of the transformer, which is what it is given, then the current which would be contributed by this generator, the transformer doesn't contribute current because it's a passive device. Active devices can only contribute to fault currents. So the current that this generator would contribute to, it would depend on the reactance of the generator as well as reactance of the transformer, which is given as 0.25 per unit. And depending on the period of interest, either XD double dash might be used, either XD dash would be used, or XD would be used. So for the different time periods that the currents are to be found out, in slide number 11 here, you would see ID double dash being the maximum value because the corresponding XD double dash is at its minimum, which is 0.15 per unit. 0.25 here refers to the transformer reactance. In the transient period, the reactance has gone up 0.25 per unit, which is XD dash here. This is XT. This here is XD double dash. And finally, in steady state, you have XD and XT. So and since the generator is unloaded, the internal EMF is rated voltage, which is 1 pu, and which is what it is mentioned here as rated voltage. So we have considered the internal EMF to be 1 per unit in all the three cases. This is all about bit A. For bit B, I had discussed in slide number 5. The corresponding RMS currents would depend on I and root 2 I value of the DC component. So the corresponding asymmetric current would be root 3 times of ID double dash. ID double dash, why? Because ID double dash is the maximum current that can appear in the subtransient period. So it is 4.33, which is 12,500 amperes on the generator side. If we compare this current with the rated current, it's almost 5 to 6 times, or almost 4 to 5 times of the normal base current. 12,500 amperes current would flow on the generator side, which is the maximum can appear. So you can imagine what sort of damage this current can create if this current is allowed to flow, because the normal generator is operating at few thousands of amperes, and now the current level in case of fault has gone up many fold times. For the third bit, we will refer to this particular equivalent circuit. For the third bit, the machine is now loaded. So we'll convert the machine, the load power into corresponding base power of 100 MVA. voltage remains 1 per unit, the corresponding load impedance can be evaluated, and hence correspondingly load current can be evaluated, which is IL. This load current is current present on the HV side of transformer. So in practice or reality, this 1 pu current would practically be referring to 144.3375 amperes of current on HV side of transformer. This is the steady state current when the generator would be feeding in a particular load. Now, in the presence of this load, if now a fault occurs, essentially a three-phase fault, that fault would depend on what is the internal EMF of the machine. So by using the corresponding, and specifically the question is about finding the generator's transient current, not the steady state current. Since the load current is already present, during this load presence, we can find what is the internal EMF of the generator. It's a cylindrical pole generator, because even if it is a cylindrical pole generator, we are neglecting the presence of XQ. So by using the KVL across the terminal of a generator which is having some transformer, then finally here we have a load. So we'll use XT and XD dash to find the terminal internal EMF with respect to the terminal voltage. The terminal voltage is 1 per unit, XD dash is 0.25 pu, XT is 0.25 pu. IL was the current which is flowing on the HV side of transformer, which is 1 per unit. So you find the corresponding internal EMF of the generator in the transient period. And once we know the transient period internal EMF, we can find the corresponding generator current, which would lead us to 2.56 per unit, because it's a short circuit fault. So load current, although it would be getting contributed, apart from this load, there is an additional short circuit path which has happened here. So you have the load current as well as IG dash current, which is flowing because of the transient EMF and the transient reactance, which is 2.56 per unit. So you can imagine, compared to 1 pu load which was there in the steady state, in transient period you have 2.56 times of the actual load. So the actual transient current would be phasor sum of both the currents, which is 3.389 ampere, which is the current which is being contributed or given by the generator to the load as well as the actual current. If we want to convert this into actual current on generator side, then we will multiply this by IB1, where IB1 is defined in slide number 10 here. So it would be almost few 7,000, 8,000, almost 9,000 amperes, in fact more than 9,000 amperes of current, which would flow in case the machine is loaded. So basically what we have done is, we have superimposed the load scenario with the short circuit fault scenario which was discussed in this particular slide, and just added those two currents by superimposition is what is the total transient current from generator to the load as well as to the short circuit fault, which is very, very large compared to the normal flow of current. That's all for today's discussion. We will understand the premise behind adding these two currents, why superposition holds true even for subtransient fault period, through the understanding of Thevenin's theorem, and we will take up the discussion of three-phase fault first, and then follow with other asymmetric faults as and when time progresses. Thank you.